Hey there, today we are going to estimate the value of 0.95 to the fifth root using linear approximation. If you're anything like me, when you see a linear approximation problem like this, you're thinking to yourself, listen, why are we approximating when I could just use my calculator? Punch in 0.95 to the fifth root in, you get something like 0.989793, so on. Linear approximations questions are really asking you, okay, yeah, but what if you didn't have your calculator? No problem. I know 0.95 is super close to the number 1. The fifth root of 1, it's going to be 1. 0.95 is a smidge less than 1, so I think the fifth root of 0.95 is going to be a super smidge less than 1. That's actually exactly what linear approximations are, except with the super fancy formula. This is our linear approximation formula. L of x, where the linear approximation equals some function f of some number a plus f prime of a times the difference between x minus a. What the heck does that all mean? I'm going to put the information that the problem's already given us in blue. We're given the fifth root of 0.95. This gives us two parts of this equation. The first part is this 0.95. That is going to be our x variable. X equals 0.95. Now we have a function here. We're doing something to that 0.95. That function is something to the fifth root. Let's call it x, because originally that's what we're plugging in, x, 0.95. The only other thing that you really got to determine here is, well, what the heck is a? A is your choice. It is a number you pick. It's up to you. Sometimes whatever a is super obvious. Here we look at this original problem and we think, oh well, 0.95 is close to 1. Any root of 1 is 1. I like 1. So here we're going to pick 1. Now what if you had something a little different? If you don't know where to begin with a and you're like, gosh, there's so many numbers, you expect me to pick 1 here, you got to look at what the function is, and that helps you pick what the best a is. Maybe you're estimating the square root of 24. In this example, your f of x is the square root, your x is 24, and the a that you pick is probably going to be 25, because you can take the square root of 25 and get that nice even number of 5, right? But if you're looking at the cube root of 24, in this case you got f of x is the cube root of x. X is 24, but your a may not be 25 here, because when you try to take the cube root of 25, you're still just guessing for a decimal. If you take the cube root of 27 on the other hand, then you're looking at a whole number. Cube root of 27 is 3, right? So like I said, what you pick for your a is probably going to depend on whatever function is going on. Okay, the only other thing we got to figure out from here is this. What is our derivative? Welcome back to calculus, yes. We have f of x here is x to the fifth root. That's the same thing as x to the 1/5. The derivative of this, bring that 1/5 down, leave the x, and we're going to subtract 1 from 1/5. That really means we're doing 1/5 minus 5 over 5. That's the same thing as 1. 1 over 5 minus 5 over 5 is equal to negative 4/5. A negative exponent really means you put it in the denominator, leave the numerator as the exponent of x, you make the denominator the root. And that's all underneath 1. If you have questions about the derivative, put it in the comments. Okie dokie. So let's plug all this in. We have L of x equals our f, which is the fifth root of a. So we're going to plug in 1 here, plus the derivative of a. So we're plugging in 1 here. And then that's going to be times x, which we know is 0.95, minus a, which we know is 1. You betcha. So this is really the setup here using that equation. Let's just work this out. Any root of 1 is just 1. Here, we do 1 to the 4th first, which is 1. Then the 5th root of 1, which is 1. So really this is 1 over 5 times 1, or just 1 over 5, times 0.95 minus 1. That's negative 0.05. This is going to shake out to be 1 minus 0.01, and that's ultimately going to equal something like 0.99. That's it. That's our linear approximation of 0.95 to the 5th root. And we know that this is probably right because looking up here, 0.9897 so on is super close to that 0.99. It's not going to be exact, but we're approximating here. So that's how we're getting a close answer. I have this other video out about linear approximations. If you want to see another example, go ahead and click there. See you in the next video.